Good morning to one and all. This is Maria Pushpam, and for today's class, we are going to see about nuclear fusion reaction and the application of nuclear fusion reaction, followed by the difference between nuclear fission and nuclear fusion. So, these are three things we are going to see for today's class. I'll repeat: what is nuclear fusion, then application of nuclear fusion, followed by difference between nuclear fusion as well as nuclear fission reaction. So first we can see what is said to be nuclear fusion. So light nuclei such as hydrogen, deuterium and tritium may be fused to produce heavy nucleus, and this process is called as nuclear fusion. Is it clear? So light nuclei such as you can take hydrogen, isotopes of hydrogen are hydrogen, deuterium as well as tritium. 1H1, then 1H2, 1H3. So hydrogen, deuterium and tritium. So these light nuclei combine together, fuse together to produce a large nucleus or heavy nucleus, and this phenomena we call it as nuclear fusion. So a typical nuclear fusion I'll explain for you. So combination of two protons, 1H1 plus 1H1, it's hydrogen, gives you deuterium, that is 1H2 plus positron plus gamma radiation. Then this deuterium combines with hydrogen to give tritium. I'll repeat. So deuterium combines with hydrogen to give helium 3. Then plus gamma radiation. Otherwise you can take two deuterium combined together to give helium 3 plus neutron. Or in other ways we can say deuterium combines with tritium to give helium plus neutron. So nuclear fusion takes place at high temperature. Therefore they are called as thermonuclear reaction. They can also be called as thermonuclear reaction. So is it clear for you? I'll repeat. So they are called as thermonuclear reaction. I'll repeat the same thing once again. So coming to nuclear fusion is nothing but lighter nuclei fused together to give you heavier nucleus is called as nuclear fusion reaction. It can happen in any way by combination of deuterium plus tritium, or two deuterium, or one deuterium plus one hydrogen. It can happen in any way. So all this reaction we call it as fusion reaction. So I'll explain the thing once again. So first step is two hydrogen combines to give deuterium plus positron plus gamma radiation, or one deuterium plus one hydrogen combined to give helium plus gamma radiation, or two deuterium combined together to give helium 3 plus neutron. If not, one deuterium and one tritium combined together to give helium plus neutron. Since nuclear fusion reaction takes place at very high temperature, they are also called as thermonuclear reactions. They can also be called as thermonuclear reactions. Now we can see what is said to be the application of this nuclear fusion reaction. We have two applications. The first one is hydrogen bomb. So coming to hydrogen bomb, nuclear fusion involves loss of mass and about 24 mega electron volt of energy per nucleus of helium is being released. Is it clear for you? I'll repeat. So nuclear fusion involves loss of mass. Loss of mass takes place, and about 24 mega electron volt of energy is being released per nucleus. So the energy thus released is about 1000 times that of nuclear fission reaction. So high temperature necessary to bring out this nuclear fission reaction is obtained from nuclear fission reaction. So the energy for nuclear fusion reaction we are getting from fission reaction, nuclear fission reaction. So during this process, millions of nuclei are fused with the liberation of tremendous amount of energy. So large amount of energy is being released with combination of this nuclei. So this phenomena we call it, this is a principle which is used in hydrogen bomb. So the first hydrogen bomb was exploded in Marshall Island. I'll repeat. So coming to hydrogen bomb, nuclear fusion involves loss of mass and about 24 mega electron volt of energy per nucleus of helium is being released, and the energy thus released is about 1000 times that of fission reaction. And for occurrence of this nuclear fission reaction, we are in need of high temperature, and this temperature is given by nuclear fission reaction. So during this nuclear fusion reaction, million of nuclei are fused with the liberation of tremendous amount of energy, and this is a principle used in hydrogen bomb. And the first hydrogen bomb was exploded in Marshall Island. Is it clear? So I have explained you something about nuclear fission followed by application. The first application is hydrogen bomb. The principle of hydrogen bomb is gathered only from nuclear fusion reaction. And next thing we are going to see is stellar energy. So coming to stellar energy, stars radiate tremendous amount of energy. If you take stars, they are radiating large amount of energy, and sun is one of the innumerable among the sun is said to be a star, and the energy released by the stars is called as stellar energy, or we can call it as solar energy. Is it clear? I'll repeat. So stellar energy, coming to stellar energy, stars radiate large amount of energy and sun is one among the stars. The energy released by the stars are called as stellar energy. Because it is star, we can call it as stellar energy, or we can call it as solar energy. The fusion of light nuclei is a source of stellar energy which occurs in two different ways. Either it can occur by proton-proton cycle, or it can occur by carbon-nitrogen cycle. Clear with the point? I'll repeat, ma. So stellar, if you take stellar energy, the energy is being produced by combination or fusion of light nuclei to produce energy called as stellar energy. And there are two types of combination. One is said to be proton-proton cycle, or its other one is called as carbon-nitrogen cycle. So first we can see about proton-proton cycle. So coming to proton-proton cycle, what happens here is, first two hydrogen atom, that is nothing but proton, combine to give deuterium plus positron plus gamma radiation. Then this deuterium combines with again with a proton to give helium 3 plus gamma radiation. Then the helium combines with proton to give you helium 4 plus positron. So this is the reaction taking place. So if you take the overall reaction, 4 protons combine to give you helium plus 2 positron plus 4 gamma radiation plus 26.7 mega electron volt. So this is the amount of energy released in this reaction. So since it is said to be the energy released, we call it stellar energy. I'll repeat the proton-proton cycle once again. So two protons combine to give you deuterium plus positron plus gamma radiation. Then again this deuterium combines with proton to give helium 3 plus gamma radiation. Then helium 3 combines with proton to give helium 4 plus positron. So if you take the overall reaction shown by the last one, fourth equation. So if you take the thing, 4 protons combine to give you helium plus 2 positron plus 4 gamma radiation plus 26.7 mega electron volt, and this phenomena we call it as proton-proton cycle. So this stellar energy can also be produced by another cycle which is called as carbon-nitrogen cycle. I'll say you that. So coming to carbon-nitrogen cycle, it leads to fusion of proton to give helium nuclei using carbon and nitrogen as the catalyst. So here carbon and nitrogen will act as catalyst. So we call it as carbon-nitrogen cycle. So first step is carbon combines with proton to give nitrogen 13 plus gamma radiation. Then nitrogen 13 is unstable, it disintegrates to give carbon 13 plus positron. Then carbon 13 combines with proton to give nitrogen 14 plus gamma radiation. Then nitrogen 14 combines with proton to give oxygen 15 plus gamma radiation. Then oxygen 15 gives you nitrogen 15 plus positron. The nitrogen 15 combines again with the proton to give you carbon 12 plus helium. So if you take the overall reaction, 4 protons combine to give you helium plus 2 positron plus 3 gamma radiation plus 26.7 mega electron volts. This is another cycle where we are able to produce stellar energy. So this cycle we call it as carbon nitrogen cycle, and carbon and nitrogen are acting as catalyst. Okay, so I'll repeat the process once again. Carbon 12 combines with proton to give nitrogen 13 plus gamma rays. Then nitrogen 13 gives you carbon 13 plus positron. Carbon 13 again combines with proton to give nitrogen 14 plus gamma rays. Nitrogen 14 combines with again with the proton to give you oxygen 15 plus gamma radiation. Oxygen 15 gives you nitrogen 15 plus positron. Nitrogen 15 combines again with the proton to give you carbon 12 plus helium. So if you take the overall reaction, 4 protons gives you helium plus 2 positron plus 3 gamma radiation plus 26.7 mega electron volt. So these are the two different applications of nuclear fusion reaction. One is said to be hydrogen bomb, another one is nothing but stellar energy. So now we can see the difference between nuclear fission reaction as well as nuclear fusion reaction. So coming to the difference, the first difference is nuclear fission reaction. It occurs in nuclei of heavy elements. If you take nuclear fission, a bigger nucleus is being splitted into smaller nuclei. So it occurs in nuclei of heavy elements. Coming to fusion, occurs in light elements, because light elements combine together to give you a big element, big nuclei. Is it okay? So that is nuclear fusion. So second point is the nuclear heavy nucleus splits up into 2 lighter nuclei. Here the light nuclei fuse to give you a heavy nuclei. Third one, it takes place at ordinary temperature. There it takes place at very high temperature. It releases energy of about 175 mega electron volt per nucleus of uranium. If you take here, it releases about 24 mega electron volt per nucleus of helium. It releases about 24 mega electron volt per nucleus of helium, and this can be controlled. Fission can be controlled and fusion cannot be controlled. And if you take this fission reaction, it is used for peaceful purpose. Fusion, it cannot be used for peaceful purpose, and the Q value of this fission reaction is found to be very low, and Q value, if you take quantity of energy released, it is found to be very high. Then the products are said to be hazardous. Here the products are not hazardous. And last one, fuel can be stored for long time. Here the fuel cannot be stored for long time. I'll repeat the difference. So first one is occurs in heavy element. There light element. Here heavy nuclei splits to light nuclei. Here light nuclei fuse to give heavy nuclei. Ordinary temperature, there high temperature. Energy is 175 mega electron volt. Here it is 24 mega electron volt. Can be controlled. There it cannot be controlled. And here fission reaction, it's used for peaceful purpose, and there it cannot be used for peaceful purpose. Here Q value is found to be low. There it is high. Then the products are said to be hazardous. Here the products are not hazardous. Then the fuel can be stored for long time. Here the fuel cannot be stored for long time. Is it clear? So I think you are able to understand what I have taken today. So we can have a short recap. So things we have seen are only 3 things we have seen. The first one is what is nuclear fusion reaction. Then I have given the example for you with hydrogen, deuterium and tritium. Then the application of nuclear fusion reaction, 2 applications. One is stellar energy, another one is hydrogen bomb. And finally we have seen the difference between nuclear fission reaction as well as nuclear fusion reaction. Thank you for listening. Continue studying. Thank you, ma'am.